if I have a function where I say like z is my dependent variable, and this is a function of x and y, then what we call the total differential is lowercase dz, and it's equal to partial z partial x dx plus partial z partial y dy. I wrote this out yesterday when we were starting to work on my favorite word problem about selling ice cream or selling Teslas or whatever it is. But this is the total differential. And let's say now that this function of x and y is such that x is a function of t and y is a function of t. Does that make sense? So I have some parameter t, and if you tell me what the value of t is, then I can calculate the corresponding value of x and the corresponding value of y for that value of t. And then having known the values of x and y at that particular value of t, then I would use x and y to calculate the value of z. So what the chain rule for multivariable functions says is that if I take this total differential equation and I want to find, let's say, the derivative of z with respect to t, then I just have to divide everything by dt. And so this is just partial z partial x times dx dt plus partial z partial y times dy dt. And since x and y are a function of t, we can calculate those derivatives dx dt and dy dt, and we know how to take the partials of partial z with respect to x and partial z with respect to y. And so this is the formula you would use to take the dz dt derivative, if you want to do that. Okay, so here's an example. Maybe I have z equals the square root of x squared plus y squared and x is equal to cosine t and y is equal to e to the power t. And so the question is, what is dz dt when t is equal to 0? So dz dt would be equal to partial z partial x times dx dt plus partial z partial y times dy dt. And we just have to find all four of those little derivatives and plug them into this equation. So starting with partial z with respect to x. What is partial z with respect to x? So it'll be 1/2 times x squared plus y squared to the power negative half, or you could say 1 over the square root, or 1 over 2 times the square root of x squared plus y squared. Then, yeah, times 2x because of the chain rule. So then those 2's cancel. And, I mean, I can simplify on the next line. Okay. Then we have to take this dx dt and multiply times, what is dx dt? And negative sine of t. And then partial z partial y is symmetric, so it's just about the same thing. It's going to be 1/2 x squared plus y squared to the power negative half times 2y, and then this dy dt is what? Yeah, just e to the t. So now we're just going to simplify this and then evaluate when t is equal to 0. So dz dt, going through here, the halves cancel with the 2's. Whenever t is equal to 0, x is equal to what? Yeah, because cosine of 0 is 1. So x should be equal to 1, and then y should be equal to what? 1, yeah. So anytime I see an x, I'm going to replace it with a 1. Anytime I see a y, I'm going to replace it with 1. And anytime I see a t, I'm going to replace it with a 0 as I go through here. So this is going to be 1 squared plus 1 squared to the power negative half times 1 times negative sine of 0, which is just 0, plus, again, 1 squared plus 1 squared to the power negative half times 1 times e to the power t, which is 1. So dz dt is going to be equal to 2 to the power negative half times 0, so that actually goes away, plus 2 to the negative half. So this is 1 over square root 2, which is also known as root 2 over 2. And so there's a whole bunch of little parts and moving pieces happening here. But I think as long as you guys can remember this total differential equation, then remember to find dz dt, you just divide everything by dt. I think you should be able to sort of navigate this one step at a time. Did you have any questions about this example? Okay, so if you had to do, let's say instead of a function of 2 variables, we have a function of 3 variables. Like let's say w is a function of x, y, and z. Then the total differential is now dw equals partial w partial x dx plus partial w partial y dy plus partial w partial z dz. And if we ended up in some situation where x is a function of t, and y is a known function of t, and z is a known function of t, if this ever happens, and you wanted to find dw dt, that derivative, then you just again have to divide through everything by dt's. And it's a slightly longer problem, but you would work it the same way. So let's do one like this. Let's say that w is equal to xy squared plus x squared z plus yz squared. And moreover, we're going to say that x is a function of t. X is t squared. Y is a function of t, and y is 2t. And z is a function of t. Well, not really. I guess z is just going to be 2 in this example. So it's a constant function. And again, what we're trying to find is this dw dt derivative is what we're trying to find, right? So we write dw dt. And so first, what is the partial of w with respect to x? Okay, so yeah, y squared plus 2xz, perfect. Then I have to multiply times dx dt. What is dx dt? 2t, yeah. And then plus partial w with respect to y. Should be 2xy plus z squared. And what is dy dt? Just 2. And then plus, now we're on partial w with respect to z, which is x squared, yeah. Plus 2yz, yeah. And then times, what is dz dt? 0. Okay. So then, really not a whole lot we can do to simplify, but we can do it a little bit. So we can say that this is 2t y squared plus 2xz, and then plus 4xy plus 2z squared. And, if we wanted to evaluate this derivative at a certain value of t, like we said, maybe let's say what about at the point t is equal to 2? Well, at t equals 2, then x should be equal to what? 4. And then y is equal to 4, and then z is equal to 2. So then you just go back here to this derivative and say if I want to evaluate dw dt at the point t is equal to 2, then this is 2 times 2 times 4 squared plus 2 times 4 times 2 plus 4 times 4 times 4 plus 2 times 2 squared. And then you could figure out what that derivative is at the point. So if you're being very astute, if you're being very observant here, you might notice that this result, though, is exactly the same result as you would get if, what if from the beginning, whenever I told you that w is equal to xy squared plus x squared z plus yz squared, and I told you that these were the x, y, and z as a function of t, you could just make these substitutions from the very beginning. You could just go ahead and make these substitutions and replace all of the x's with t squared, and you could replace all of the y's with 2t, you could replace all the z's with 2, you would actually get exactly the same answer. So this chain rule for multivariable functions is not incredibly useful. Like, you don't really have to use it if you don't want to, right? I mean, if I gave you a question like this on an exam, you could just substitute in these expressions for your variables and then just take the derivative as if it were a single variable function, and it works just the same. But now you know it exists. It's a different way to do it.
For very complicated expressions.
Yeah. Yes, I think it would. I think if you're right, if these functions of t were really, really crazy, then maybe it helps you to partition your work into smaller bite-sized increments. Yeah. Okay, so that's the chain rule for multivariable functions. The other thing in section 13.5 is implicit differentiation. So, let me find an example. Like this one says secant of x times y plus tangent of x times y plus 5 equals 0. And you probably worked a problem like this in Calculus 1. I mean, the one time I taught like Calculus 1, I ended up teaching implicit differentiation with two variables like this. But what we're trying to do is find, from this relation, find a formula for dy dx. So what's the derivative with respect to x of this first secant of xy? Do you know?
We got x, going to be y secant tangent.
Yeah. So the derivative of secant is secant times tangent, right? So it would be secant xy times tangent xy. And then the chain rule, the derivative chain rule, says I need to multiply by y, because we're pretending y is a constant when we take the derivative with respect to x. So again, what I'm doing in this step is everything I'm taking the derivative with respect to x. And then what about tangent? What is the derivative of tangent?
Secant squared.
Secant squared, yeah. So this will be secant squared of xy. And then again, the derivative chain rule says I need to multiply by y. And then the derivative with respect to x of 5 is 0. And the trick with the implicit differentiation stuff is that we assume that, well, this is a relation between variables x and y. And so if I want to consider x as being like an independent variable, and that means y is kind of like a function of x. So we actually make another application of the derivative chain rule here. And we say that we are going to consider this x times y inside the secant as kind of like a derivative product rule, right? This is like an x function of x times a y function of x. And I didn't leave myself enough room. But basically, instead of just saying that the derivative of this x times y is y, a constant, what we're going to say is this would be f prime g plus fg prime. So 1 times y plus x times dy dx. And then over here, again, instead of having that y there, we're going to treat the xy on the inside argument of the tangent like it's a product of two functions of x. So the derivative product rule would say, again, this is y plus x dy dx. I wasn't thinking ahead, so I didn't leave room, but let me rewrite this. It should be y plus x dy dx times secant of xy times tangent of xy plus y plus x dy dx times secant squared xy equals 0.
Can we call this like expression z and then set dz dx and then put it equals 0 to derive x? Like apply the total differential formula.
Maybe. Try it. Try it and see if you get the same answer. So here we can think about dividing both sides of this equation by secant, right? So 0 divided by secant is going to be 0, and then this is going to simplify down to I'm trying to isolate the dy dx by itself. Times tangent xy plus secant xy. And so, again, I could divide both sides of my equation by tangent xy plus secant xy. I'm going to get y plus x dy dx is equal to 0. So then dy dx would be equal to negative y over x. So if you know values x and y that satisfy our initial equation that I gave you, the secant xy plus tangent xy plus 5 equals 0, if you know values of x and y that satisfy that, that original equation, then you can plug in those values of x and y to find out what the slope of that curve should be in the plane. Let's give that a shot. Just check our work, see if we did everything right. So I think initially I had secant plus tangent plus 5. Okay. So now what I want is a line. And so what I'm going to do is make a point here on Desmos. And then I'm going to write the equation y minus k equals m times x minus h. So that's just point slope form of a line. And then the slope of this is going to be equal to negative k over h, right? It was supposed to be negative x over y. Okay. And so now if I put this point on anywhere on the red curve represents the solutions to my original equation, then this should give me a tangent line to the curve. Okay, and it looks like we did everything right, because if I move this point along the curve, then it gives me tangent lines. We're going to set z equal to all of this. And then dz, my total differential, is going to be partial z partial x dx plus partial z partial y dy. And then since we're trying to find dy dx, I have to rearrange this equation until I can get like dy over dx. And
divide by dx and then set equals 0.
that gives me dy dx. And so then I subtract, oops, that, and then I would need to divide everything by partial z partial y. To get dy dx like that.
Yeah, but we need to take into account that z is 0, so dz dx is 0.
Z is 0. Yeah. So you're right. Yeah. So up here in this equation right here, we basically just said z is equal to 0. So any true full derivative of z has to be constant, right? Well, I mean, this is constant. Z equals 0 is a constant, so the derivative is 0. Yeah. So then that goes away to 0. Cool. So if we were doing it this way, what you need to find is negative partial z partial x over partial z partial y. So what is partial z with respect to x? That's supposed to be partial. Partial z with respect to x, not z. So this way, I am considering y as a constant and not at all as a function, right? So looking at this and then considering y to be constant, this is actually going to be y secant xy tangent xy plus y secant squared xy.
Since it's symmetric, it's gonna be them.
Yeah, you're right. So I don't have to think too hard about the denominator here. And so this would just be x secant xy tangent xy. Yeah, and then so these would cancel and get negative y over x. Yeah, cool.